Good morning. I'm going to continue discussing the fine structure constant. The fine structure constant, sometimes physicists call it 1 over 137. City College is on 137th Street and Broadway. It's a stop, well, it's close to there. So, you know, that's by fate, because City College was a great university one time, it still is. Some of my great teachers were up there. Professor Gerson, Boyer and Nair, I can remember, were great teachers. Okay. Although I mostly learned myself, I have to tell you guys, learn most things yourself. So the last day, we talked about the fine structure constant. It plays a very crucial and mysterious role in nature. Why it has the value it has, we don't know. Why all those things, E, a charge on the electron, the H and the C, and the epsilon zero, the electric constant come together, well, that's a mystery. We don't know why they all do that. And they come together in a dimensionless way. So today we're going to work out the value of the constant, work out the units of the constant, and show that they're dimensionless. What else will I do? I'll talk about Stoney units, actually. And it's a live calculation. If I make a mistake, you can call in. My email is droiley@physicist.net. Now, the last day, we worked out that the energy levels in the hydrogen atom, the principal energy levels, there's no fine structure here. The fine structure constant first came up under Sommerfeld in 1916, as I said the last day, when he tried to look at the finer details of atomic spectra and improve the Bohr atomic model. So I'll talk about that maybe at some stage when I have time, but right now I just want to keep things as simple as possible. But the constant, it still crops up in the energy levels of the hydrogen atom. Now, in the hydrogen atom, the Bohr atomic model says that the electron goes around the nucleus, and in the hydrogen atom it's just a proton. It orbits, and the orbits are made up of integral number of wavelengths. I made it a circle. But you can have higher levels and lower levels. But they're discrete. And in this one here, we'll have, let's say, one wavelength going around, two wavelengths, three wavelengths. And the electron could fall back. When it falls back, it emits a photon of light. And the photon of light carries energy h times nu. HF is what you see in American high school texts and even college texts. H is Planck's constant, F is the frequency, okay? So, the energy of these particular levels, the ENs, is given by this formula, okay? Now you want to subtract the levels, depend if this electron falls from here to here, the energy of the photon, and gamma is the symbol for a photon, will be E2 minus E1, the difference in the two levels. If a photon falls back from here to here, energy is going to be E3 minus E1. We want to conserve energy at all times. Okay, so this number here is known as the fine structure constant. Now I want to focus in on this simple formula. We worked out this. You can go back to the first lecture on the fine structure constant to see where it came from, see how we worked it out, right? We used Coulomb's law, centrifugal force, I like that word, not centripetal, and energy. The energy being the sum of the potential plus the kinetic energy. Actually, the Varial theorem could be put in there too, but that's too complicated. All right, and there's an n here as well. Okay, so the n is the integer, and there's a half, and there's an m0 c squared, and there's a fine structure constant. Now the quantities in here are the fine structure constant, the integer, the rest mass of the electron, and the speed of light, which is 3 by 10 to the power of 8 meters per second. This is what it's saying. The energy levels are proportional to m0c squared. Let's say n equal 1. When n equals 1, we say that the energy, level number 1, is proportional to mc squared. Wait a minute. This is profound. Why people don't yell at this when they write textbooks to me is a mystery. I never mentioned relativity in this. E equals mc squared is derived using the postulates of special relativity and the idea of the Lorentz transformations. Okay? And the expression for momentum, the relativistic expression for momentum. E equals mc squared. Now, wait a minute. I never mentioned anything relativistic here. This is just the idea of a quantum, and the principles of de Broglie, Bohr, centrifugal force, and Coulomb thrown in together as a model of the atom. And out I get that the mc squared is in there. That's and then the dimensionless constant. Okay? That is profound right there. That's enough for this lecture. If I just told you that, that's absolutely wonderful. Now, let's focus in on the fine structure constant itself. I shall leave a circle on the board, actually. This is very good. Pellegrino, am I doing an advertisement? Better than beer. All right, alpha, the fine structure constant. Is given by E squared over 4 pi epsilon 0 h cross c. Sometimes people write it down like that, but these are adjusted units, and then students go away to see why is it not dimensionless, but they forget that this E is E dash. If you see that in there, you have to replace the dashed E by this one, the adjusted one. Now, let's see all the quantities in here. E is the charge on the electron, 1.6 by 10 to the power of minus 19 coulombs. Epsilon 0. Is the permittivity of free space. Now I can write this expression in 3 different ways because I could write it with the epsilon 0 replaced by a c squared and a mu 0, etc. This is the magnetic constant, the permeability of free space. This is the speed of light. See, I make a mistake. And I can rewrite this in lots of different ways. I leave out this computation. Okay, I'll leave it there. Now, H cross is the reduced Planck's constant, h over 2 pi, 6.626 over 2 pi, 1.054 joule seconds. And c is the speed of light. Okay? 4 pi is dimensionless. So let's do units. Because I want to put in the numbers and I don't want to be throwing the units all over the place. E squared is going to be coulombs squared. Okay? 4 pi is dimensionless. Epsilon 0 is coulomb squared over newtons meters squared. H cross is joules seconds. Now a joule is the same as a Newton meter. Newton meters, seconds. And C is meters per second. So let's see what happens to the units. Well, the first thing is that the C's cancel. Now the Newton meters here goes that into that a meters times. And the seconds cancel. Okay, so what have I got? I've got 1 over meters, which is 1 over 1, which is dimensionless. One over 1, so just 1. So that's for the units, and these are the objects. Now the next thing is we put in the numbers. Okay, for this one here, so we'll say that alpha is going to be e squared over 4 pi epsilon 0 h cross squared. With just 1 as the units. We put in the numbers. On the top we have 1.6 by 10 to the power minus 19 squared. We have 4 pi. 4 times 3.141, whatever it is. Epsilon 0. (8.85 by 10 to the power minus 12). H cross. 1.054 by 10 to the power minus 34, and C. So we gather up all those numbers. 1.6 has to be squared. Four pi times 8.85 . We gather up all the numbers on the bottom, and then all the powers of 10. Well, we have on the bottom minus 12, minus 34, plus 8. Okay, so far so good. And we get all the powers of 10. 2 19s is negative 38. When I bring a 12 upstairs, it becomes positive 12. Negative 34 becomes positive 34. And positive 8 becomes negative 8. Now I did this before, and I don't want to go through it all again, so I just throw the number in. When I work out this number, I get 0.07299 by 10 to the power of, well, you can see this, 38 minus 34 leaves positive 4, sorry, negative 4. Negative 4 and positive 12 is positive 12, positive 8. Positive 8 and negative 8 gives me 46 minus 46, which is 1, okay? Now your calculator will throw out lots of other digits. We don't need to do that just yet, we'll just hang on to this. So let's see where we've gotten. rid of some garbage. Now you can go and check my calculations. If I made a mistake, you can email me. I mean a big mistake. I don't mean if I've just got an 8 here instead of a 9. Something significant. Now some people like to write this a different way. Now I don't know what the decimals of that are. There are some decimals here. You can look at it. This will do. You can check it up yourselves. Approximately this number is going to be 1/137. That's the way physicists like to remember it. Right? Now, what can I say about this? Oh yes. We're going to say that this is equal to g squared. So that g actually I want to use this. G is the square root of 0.00727999. I would like people to start memorizing the fine structure constant more like this number than this one, but it's traditionally done this way. So G squared is this. Now what is G? G G is the probability amplitude for an electron to emit or absorb a photon. In other words, if an electron is coming along, minding its own business, it emits a photon. Well, you know when you throw away a billiard ball, something, for every action there's an opposite reaction. So instead of going in a straight line, the electron detours off in a little direction and the photon goes out that way. Of course, the opposite could happen. The electron could be going off in this direction and a photon comes and bombards it. Now this is proportional to G. Alright? This probability amplitude. Now sometimes you can have an electron going along minding its own business and another electron comes over here and the two of them come close enough to interact. This guy emits a photon and this guy absorbs it. But we have a probability here and we have a probability here. And the probability amplitude for this event to happen is proportional to G squared. Does that look familiar? Well, it should do. It's a Feynman diagram. Richard Feynman was one of our great physicists of all times and great characters. Actually, I was involved in the Tubman Society. I have a couple of stories about that with Bob High, the late Bob High in New York City, and bringing the throat singers. Maybe I'll do a bit of throat singing here for you guys someday. Okay. So Richard Feynman lived between 1980 and tragically died at the age of 70 in 1988, just after the space shuttle disaster in 1987, and he contributed to the investigation, as everybody knows, A lot of people remember his last contribution, which he did in cooperation with some general, and I forget the general's name. It's a Polish name. Maybe for the next class I'll talk about that. One way or another, this is what this G is. It's related to the Feynman diagram. The probability amplitude is the square root of R1 over 137. And that's our alpha. So that's what we've done now. We've talked about the fine structure constant as it comes into quantum electrodynamics, right? First of all, we talked about the fine structure constant as its role in the simple model, the Bohr model of the atom. And we got E equals mc squared, incredibly, without doing any relativity. And now we see how it's cropping up in the perturbation theory associated with quantum electrodynamics, okay? Actually, maybe I'll do a class on renormalization. That's interesting. Okay, so let's continue. There's one more thing I want to do with the fine structure constant today, and then I'll do it in greater detail in the next class. And that's to do with units. So this is coming off the board. Now, another great and unsung hero of natural philosophy is George Stoney, 1826 to 1911. He did many things. He recognized the electron as the fundamental unit of electricity. He named it such, slightly different form of the name that was used, but he did many other things as well. In particular, he came out with Stoney units. Let's see what happens when we take the Planck length. Now, I have derived the Planck length for you guys in a previous lecture. If you look it up, Dermot O'Reilly, the Planck length, not the length of a Planck, is related to Max Planck and his set of fundamental units. Now, the Planck length is given by, and I derive it, the square root of GH cross over C cubed. Let's make sure I did that right. Oh, absolutely, I forgot to do one thing. I forgot to derive, I know I did that, that's fine. Let's see what else I did. Okay, so we're looking at GH cross over C cubed. Now if I multiply root alpha times LP, I get root alpha I get this quantity here. Let's write it all under the square root. Okay, what I do is I get rid of the Planck constant. Planck's constant crops up when we go quantum. In George Stoney's time, in 1883, there was no H. No H was known then, but the charge on the electron, well, they hadn't figured it out yet, but it was coming up anyway. J.J. Thomson measured the charge on the electron. Let's see what happens. Look, H goes away. I get a new fundamental unit of length. We're going to call this the Stoney length. George Stoney, before his time, in 1883, in the Proceedings of the Royal Dublin Society, published this little paper, where he talked about Stoney units. I'm going to do a whole set on units, because we can get the Stoney time, the Stoney mass, and Stoney charge, units of everything which are Stoney, before the Planck units, and they're just as fundamental. Does that mean there's no H cross? Yeah, maybe. Maybe these are the guys that are important. Maybe the E and the G and the C are the things with the epsilon zero that are important. And I can always replace epsilon 0 with the magnetic constant and another factor of the speed of light. There are lots of ways to write this. And no h is included. Okay? Now that's profound. Anybody out there want to see why that is? You can play around with algebra. You don't need big calculus for this. You can play around with just these symbols. I'm going to give you more. I'm going to give you lots of other formula that if you just know 7th grade mathematics, you can go away and play big physics. Maybe you'll come up with something. If enough people did it all the time, maybe we get something profound as an answer. Paul Adrian Morris Dirac did stuff like that. He played around with large numbers, constants, to see what, if you move them around the place, what information will we get, okay? Now this is the Stoney unit. We can go find the Stoney mass by multiplying the Planck mass by root alpha. We can find the Stoney time by multiplying the Planck time by the fine structure constant. Now today I've given you a lot of profound things, there's more to come. I have to finish up the covariant derivative. I didn't do that one yet. I didn't get around to finding a simple way to do it. When I find a simple way to derive the expression for gamma, I'll finish up the covariant derivative. As of yet, I haven't. It's just big, long ways to do it. That's enough for today.